Okay, welcome to another fun-filled afternoon of mathematics involving standard deviation. What I want to talk about today is a real-life use for standard deviation, and this is an example of how in industry standard deviation can be used to determine which option would be most cost-effective when setting up a machine to produce components. Doesn't matter what those components are, obviously different settings gives you different quantities of goods. Faulty goods cost you money, so therefore we need to know whether the cost of faulty goods can be offset against actually spending more on fine-tuning the setup of the machine. So let's look at the question. The question says, a machine produces components in batches of 20,000 and their lengths are normally distributed. Now remember normal distribution, we talk about normal distribution. If we was to plot values for the components, the lengths of the components in this case, though the normal distribution means we get this what we call a bell curve. In other words, the graph that we can plot, the curve that we can plot, will be a symmetrical bell shape. Okay, so that's what we're talking about with normal distribution. Okay, each component has a required mean length of 15 millimeters, and the machine can be set to give one of three different standard deviations. Those standard deviations are, well, first off, 0.06 millimeters. Secondly, 0.075 millimeters, and the third option is 0.09 millimeters. Now, the cost of setting these standard deviations varies, with the cost being higher when the standard deviation is smaller. Obviously, that's when you're going to get, a certain amount of wastage with that standard deviation. Obviously, when the standard deviation is larger, you would potentially expect there to be more waste. Okay. When the machine is set to be more accurate, these costs are option one. If you want a standard deviation of 0.06 millimeters, then the cost will be £850. If you want it to be 0.075 millimeters, the cost is going to be £550. And if you're quite happy for the standard deviation to be 0.09 millimeters, then you're going to end up with a cost of £100. So they're the different setup costs. Any lens that is produced must be within a certain range, a certain tolerance, and that range is it has to fall between 14.82 millimeters and 15.18 millimeters. Otherwise, it's classed as being defective, and every defective unit is going to cost the company £1. Okay, it's going to be a wastage of £1 for every one. So the question is, which of the three options is the most cost effective for producing a batch of 20,000 units? So where do we go from? Well, let's have a look. As I say, we have our normal distribution curve, okay, to do with our standard deviation, and as you can see, we've got the mean. The mean length is 15 millimeters. We have a lower length of 14.82 millimeters and a higher length of 15.18 millimeters, and anything outside of this range is going to be classed as defective and cost the company money. Okay, so that's how it would look as a graph. So let's have a look at option one. Option one, well, we've got a mean of 15. Well, it's going to be the same for every option, as it's going to have a mean of 15 millimeters. Standard deviation for option one, though, is 0.06. So what we do is we find the z-score for the lower limit, and we find the z-score for the higher limit. So we find the z-score for 14.82 millimeters and the z-score for 15.18 millimeters, lower limits and higher limit. Okay, and as you can see, lower limit, upper limit. If we find the z-score for the lower limit, it will tell us the probability that a unit will lie to the left of this value. In other words, will be defective. If we take the z-score of the higher limit, what we find is that it will tell us the probability that something will lie to the left of this, which will include the good and this defective. So if I take this value of the higher value and I subtract the lower value, Z score, what I will have then is I will have the probability that a unit produced will lie within this range and be a good unit. So that's the first thing I'm going to do. So if I look for the Z score for the lower limit, 14.82, remember how we find the Z scores? We take what we're looking at, the limit we're looking at, which is 14.82, we subtract the mean score, which is 15, and we divide it by the standard deviation, which in this case is 0.06. And when you do that, 14.82 minus 15 all over 0.06, you will find you get an answer of -3. When we take the higher limit, well, we do exactly the same, but this time the higher limit, it was 15.18, so we subtract 15, divide by 0.06, and we're left with an answer of 3. When you look these values up on the Z tables there, when you look them up, what you'll find is that -3, okay, is on a Z table 0.0013, okay, which is 0.13%. So there's a 0.13% that something is going to fall outside of that lower limit, i.e. to the left. If we take the higher limit, what we find is that the value, the probability that something is going to fall to the left of that higher limit, let's have a look back on my little drawing, anything to the left of here, well, the percentage of components that are going to fall within that, left of that limit, is actually going to be 0.9987, which is 99.87% of components will fall to the left of that. Like I say, subtract the lower from the higher, and that will tell us the probability that a unit will fall within the range that is classed as good. Okay, 0.9987 minus 0.0013 will give us 0.9974. We now know that 99.74% of components made with this standard deviation are going to be good. So how do we find out which ones are bad? Well, if you remember, with probability, everything, good and bad, added together will give us a probability of 1, 100% or 1. So if we take 1 and we subtract the value that we got for good components, 0.9974, that will tell us the probability that one of the components produced with this standard deviation is going to fall within these defective areas here. Okay, so 1 take away 0.9974 will give us 0.0026. So the probability that a component with this standard deviation setting is going to be defective is 0.0026 or 0.26%. How do we find out how many defective components have we got then? Well, the way we do it is we take the probability that one of the components is going to be defective and we multiply it by the amount of units produced. And the amount of units produced is going to be 20,000. So if we take our 0.026 multiplied by 20,000, we find out that we're going to have 52 defective units. If you remember from the original question, we were told that each defective unit costs a company £1. So if there's 52 defective units, that's £52 that is going to be a cost to the company in wastage. So we've got £52 for wastage for faulty components, plus the setup cost was £850. So the total cost of option 1 is 52 plus 850, which is £902. So option 1 will cost us £902. Let's do the same process